All right, part 3. What fun. So I took this out in the yard and just sprayed it down with the garden hose, and it took all the dirt off, but I mean, it's still, you can still see we need to do more cleaning. But it did make it a lot better than it was. Now you can actually see the corrosion from all that, how it's been stored and everything. So this is, as I said in the last video, I'm going to strip this all down and then spray paint it. This may need the same treatment, although it's not as bad. The chassis itself, if I can fit it up here on the bench with all this other stuff here, it's not bad, but if you look up here, there's a little bit of corrosion area in here. Some of this will clean off, but not all of it. And there's small amounts around here, but I'm not going to repaint this whole chassis because that's just going to be too much work, and I don't really want to do that for this. It's all inside. I will make sure that it doesn't get any worse. I'll clean it properly and everything, and maybe put something on it, top coat or something, to keep it from getting worse, but that's all I'm going to do. Now I have a feeling these capacitors are still good, and I don't know if I want to test them and then, put them back in. They're only 63 volt caps, so I should be able to find some good replacements. I did find some that somebody used in one of the forums out there, and you can still buy them, I believe, at DigiKey. But you're talking about another almost $100 worth of capacitors, because they're 20 some dollars a piece, plus the shipping and so forth. So I don't know if it just that it keeps adding and adding and adding to the cost of this restoration, and at some point in time you just have to draw the line. So if these are in perfect condition, I'll keep them. If I have 4 63 volt caps at 12,000 microfarads or above, and they can fit in here without a ton of modification, maybe I'll do it, but I'm not sure. I think what I will do, though, is I will test these, and I'll go through the process of how to test a capacitor. It's not going to guarantee anything of how long it'll last when they're old like this, but it will at least tell you if they're currently in good condition, and whether it would be a safe bet to continue using them, or whether it's a better choice to replace them, even though you have to make that investment. So maybe that'll be something we'll do in this video. But let's get this thing torn apart first so we can see how it's assembled. You can see that it's kind of unique how this is put together, and you really will be able to see better how this is all linked to the board when we get this out. So let me finish taking these brackets apart, and then we can slide everything out the bottom and show you what it looks like. Okay, our first problem is, even after taking all the hardware off of here, these metal bands are just fused to the plastic outer case of the capacitors. So I'm going to have to remove this and just kind of bend them to get them to pop loose. You can see how badly stuck they are in there. I'm even trying to use a spudger to get it apart, but it's almost like they're glued in there. I don't know if you could see that, but they may have put glue or something, but you cannot get this off. Look at that. There. And then the only thing I can do would be to bend this back into shape. So I don't know if that's on purpose or if that's just crud, but you can see. So I'll wash this off, and I might spray paint this, and then we'll bend it back into shape. But wow. Yeah, that looks like somebody put double stick tape on there, which I don't know why you would need something like that for this. That's kind of crazy, but this is what you're going to go through if you take this thing apart. I'll take that off. Yeah, I was just going to originally, where I was going to go with this video was talking about, we were just going to clean all these things and then disassemble them and start the restoration, you know. But I think it's going to be better on this video because I'm really in no hurry to get through this series. We'll do a little section on testing big filter caps to see how they'll hold up. And again, there is no forecasting really. I mean, I know you can, you know, there's different tests and things you can do, but you really, no one knows how long a used old capacitor is going to last. They could last many, many more years, or they could fail. I've had ones that just had a long shelf life and were new old stock, and they formed up okay when I first, you know, brought them up. They had a little bit of short circuit when they formed. They got hot. But then after that, they settled down. They were perfect. And then after using them for a couple hours, they shorted. Just dead short. So it happens. All right, so you can see how they do this on this. So you have this, the bottom of the board here, and they make contact here and here. And they have these little adapter tabs they put in, and you can see they're kind of corroded, not making very good contact. So if you replace those, you're not going to find this type of capacitor case anymore. They don't exist. The screw terminals are always larger. We're talking like M3 to M4 sized screws. These are smaller. These are more like an M3. And so you will have to modify these brackets and perhaps even bend them a little bit to get them to fit into the board. I know that's what's going to happen, unless we can come up with some other solution, which I have a couple of thoughts, and we'll see that as we go along. But maybe these are perfect. I don't know. We'll test them. Okay, so let's do some capacitor testing. And as you can see, these are 63 volt, 12,000 microfarad capacitors. They're 85 degrees C, and I'm assuming they are plus 20%, minus 10% as far as the tolerance is concerned. So the first thing we're going to do, since we have it, is we're going to use our LC102Z meter. And the camera is a little bit shaky where it's on the stand, so if it wobbles a little bit, that's why. And I hopefully have this focused. Let's see. About as close as I can get it. All right. So what I've done is I've typed in all the parameters of the capacitor already. And if you look over here, I've connected the first one. And it's going to allow us to test a whole bunch of things at once, very simply. So first thing we want to do is look at the value. So if I go down here, I hold this in, and you can see it's reading about 9,300 microfarads. So it's a little bit depleted. And of course, that's more than 10% low, so we got a bad sign there. You can see that. Capacitor leakage. This is the same as my standalone leakage meter. This can apply the full 63 volts to the capacitor, and it will check for any kind of leakage in the capacitor. So if we do this, it takes it a second to charge up. And you see that's going to flash while the capacitor is charging, because there you go, it went good. And you can see if I keep this on here long enough, the leakage is going to get smaller and smaller and smaller with time. So for this type of capacitor, that's not too bad. And you can see it'll just keep going down. Now, and that little beep you just heard, that is the discharge, because there's an actual discharge circuit in there that will discharge the capacitor for any other test. And you want to make sure that you get a 000 and that beep before you try to do another test. Okay, the next thing we'll check is the ESR, or equivalent series resistance, as my camera jumps around. And you can see the ESR is 0.39 ohms. So it's jumping around a little bit, but it's good. And then we're going to look at the dielectric absorption. Now this is something that not very many pieces of test equipment can test. Dielectric absorption is the property where a capacitor will self-charge because of the chemistry in it. It's a big deal in electrolytics a lot of times, and you'll see that some of these big electrolytics can have quite a bit of dielectric absorption. So if we hit this button, and it's going to sit there and kind of start with a clean slate, and then it's going to check. And you can see it's only 9% on this, which is good. So other than the value of this cap being a little bit low, according to our LC102, this capacitor is good. So let's go over to another one here. And again, it is depleted somewhat. So let's see what this one looks like. Same test value. It's better. At least it's over 10,000 microfarads, but it's still out of its tolerance, just barely. Leakage. That's good, and it'll just keep dropping. Let it discharge. Okay. ESR. Again, it's good. Same as the other one, just about. And the dielectric absorption. And you can see that one's high. So, not so good. So you can see they're all kind of reading differently because they're old. And I've had these powered up a good bit testing this thing, so I can't say that it's just that they need to be reformed. Okay, that one's about the same. It's 10,000. Leakage. That one took a little longer, but it's okay. Let it discharge. ESR. See if it's about 0.4, and it is. And then dielectric absorption. And again, that one's even worse yet. All right, so now I'm going to go to a brand new cap, and these are very similar specs, even though they're physically different size. They're the same spec, and they're still Nippon Chemicon. And these are 80 volt instead of 63 volt. But we're going to test them as a 63 volt, so actually we're going to be a little easier on it. But we can actually change that. Let me go up here. Let's see here. 80 volts. There we go. So now this one's set. So let's test it and see how it tests out. Value. Oh, I'm sorry. This one is 22,000. I'm wrong. These are 22,000 microfarads. You see that? And these ones are 12,000 microfarads. So, yeah, I need to reprogram that. So, 22,000 microfarads. Okay, now it can test it. And that one's reading a little bit low also, but it's close. It's reading about 18,000. And again, it may be that this one, these ones aren't formed. They've been sitting for a long time. Leakage. The higher the voltage you're testing at, the longer the leakage test takes to do because it has to charge up. And it's current limited the way it charges it, so it's not gonna, it just takes a while. And this is double the capacitance of the other ones. You see there, now it's going to drop, and it's really good, and it's dropping quickly. All right. Okay, and ESR, very good on that. It's actually a wee little bit higher than the original ones. And dielectric absorption. Again, this was one here that fails a lot on these big caps. You could see that, 36%. So there you have it. So it's very similar to the original ones. And I would say if I tested the other three, you're going to get similar results. Okay, it is another day, and I want to do some comparison with the LC102. We're going to use this DE5000 LCR meter because these use a little different technique of testing. We'll see how they agree. The other thing is, remember it wasn't yesterday, it was 2 seconds ago for you, but yesterday for me, when we used the LC102 and we measured the dielectric absorption. And if you remember, these were all discharged because there's a discharging circuit in there that keeps the capacitors discharged when you're done testing them. These have been sitting overnight. I've not connected them to any power source. They've just been sitting out in the open like this. And I've just taken the meter here. And let's just measure to see if any voltage has developed across these caps. So you can see there, 1.57 volts. How about this one? 1.68, even higher. How about this one? 1.68. 1.16. See that? How about these new ones? Doesn't matter what way I put these probes, but 2 volts. Wow. This one's 0.2 volts, and this one's not so bad. So we'll put that aside. 1.3 volts. And 1.97 volts. So you can see the dielectric absorption. This is the only one that didn't really gain a lot of capacitance. Now, you may want to do that before you connect something like this. The LC102 has its own built-in discharging circuit that can deal with a charged capacitor. This doesn't. You don't want to put a charged device across this. So we're going to have to, of course, we're going to have to discharge it. So what I'm going to use is just my little stinger cable. It's just a resistor and a wire. And I'm going to make sure this thing is discharged so that the meter will work. So I'm going to sit here and let's measure now and see what happens. Okay, now it's discharged. How do you like that? So let's put this on here. And you have to do this with all of them before you test them with this kind of a meter. Okay, so again, this is a 12,000 microfarad, and it's saying it's about 9,000, which is agreeing pretty much with the LC102. Now, here's the thing. We're measuring this at 120 hertz. And on this one, you have variable test frequencies. And you'll find that depending on what test frequency you use, this is going to change. So, for instance, if I go to 1 kilohertz, you can see it's already having a hard time reading it. If I go from parallel to series, it still won't read it. So you can see, depending on, and as you go up in this, it's just going to not want to read. Switching back to 120 hertz, we can read it again. So how these things, test a capacitor can affect the reading that you get. So when you read this on here, you really have to look at the data sheet to understand how they're deriving these numbers here. as far as how many microfarads, because it changes with frequency, or at least the relative capacitance, let's say, because of the way it tests it. Let me discharge this once again, just for fun. And let's put this on capacitance and see if this can, I don't know if this can read that high or not. I don't know if it can go to 12,000 microfarads, but let's see. Yeah. And you can see this reads a lot closer to what the capacitor says, 11,200 microfarads for a 12,000 microfarad capacitor. So you can see that the test signal that it applies, because really all you're doing is you're applying a signal to the capacitor, and then you're measuring the time constant of that signal. And that's how it's determining what the capacitance is. So depending on the frequency, depending on the internal resistance of the meter that you're using, all kinds of things, it will affect the reading that you get of the capacitor. And this is mostly, you're going to see this on high value electrolytics. That's why they're not that easy to test. So it's really hard to say whether this is a good or bad cap unless you really test it thoroughly. Okay, next thing we're going to do here is we're going to do a leakage test when we do not have a leakage meter. And this is going to put full power across the capacitor, and we're going to charge it up to its full 63 volt potential, and then we're going, or close to it, and then we're going to see if there's any leakage on the meter here. So all I've done is I have put the leakage meter and the capacitor, and this is an amp meter, so this is measuring amps. There's a shunt between here and here. So what it's going to do is the power supply, and this power supply can go up to 120 volts DC, it's going to charge the capacitor through the amp meter. And as it charges up, once the cap reaches proper voltage, the current should drop to 0. And then we can go down to microamps and actually measure any leakage that may be there. So let's do that. And I'm going to do this slowly because this can only handle 400 milliamps of current when it's in milliamp mode. So I'm going to just turn this up very slowly. And you can see how it kind of jumps as you do that. You could also put a resistor in series with this to limit the current. You can see even right now with 11.5 volts, I have 64 microamps of leakage. Now we have 100 microamps. So you can see this is a little worse than what we were seeing with the LC102 leakage meter. Let's just keep going. Let's just keep going up. And let's go up to about, and I have, like I said, I have the current limit set on this. There's 61 volts. And you can see there's 2 milliamps of leakage. We're just going to let this go here and see if it forms, and see if the capacitor forms up. Now, the LC102 has a very current limited supply in it. So when it does the leakage test, it limits out at just a few milliamps, whereas this thing can put up to like 3 amps, I think. It's current limited right now, so it won't let it go that high. But, you know, because you can actually set how much current you want to flow maximum. But 400 microamps is a lot of leakage. And that could pass noise into your signal, into the amplifier. All right, let's disconnect this. And let's turn our voltage back down. And I'm going to discharge this. And let's see if I can find a different gizmo to do that with. Here we go. Just see how much fun this thing is. Okay, and I got it in 80 volt. And let's discharge this thing and see what we get. There it goes. Okay, it's discharged. All right, so let's go to the next one here and see what it's like. So this one had some pretty considerable leakage in it. So let's now go to this side. And let's see what we get here. So it's limiting the current. It's not letting it get up anywhere near that 400 milliamps with the current set where it is. So we can go a little faster this time. All right. And again, you can see we have about 2 milliamps. And it'll probably drop a little bit more over time. And again, as these form up, maybe a little bit more. But a milliamp of leakage current is quite a bit. And again, there's nothing in the circuit, across this or anything you can see. And by the way, with these types of Chinese power supplies, they don't have a lot of protection on the front end. Don't go turning the voltage down with this capacitor attached across it. That may cause damage. Don't do that. Notice how I disconnected the lead before I turned that down. So we can see this is dropping. We now have 700 microamps. But that's still a good bit of leakage. Okay, let's disconnect, turn the voltage down, and discharge. Let's see here. And there we go. Okay. All right, let's try one of these new ones and see. Actually, let's try this one that had the low dissipation factor. Let's see what it's like. And this is an 80 volt cap, so we can go higher on the voltage on it. But we'll try it at 61 volts. Okay, here we go. You can see it's limiting the current to about 65 milliamps. And there's 60 volts right there. We'll go to our 61 volts just to make things fair, 61.4. And you can see our leakage on this one is about 2 milliamps. And we'll give it some time to see if it forms up. These capacitors have been sitting for a long time, so they may need to form up a little bit. But as you can see, there is leakage. It's dropping. Doesn't seem to be much better than what these other ones were. Let's go up to 75 volts. Not bad. Okay, so you can see when you use a basic test setup like this, it actually shows you some things that in the real world, when you put a real power supply with heavy current, well, heavy current, this one's limited to 60 milliamps, you can see that you will get leakage. And of course, this is a 22,000 microfarad also, so that's a lot, almost double the capacity. But it's dropping down. Okay. Turn this back down. And once again, let's discharge this. So once you get up around 80 volts, you would feel it if you got your hand across it. So, and of course it would melt things. And there it goes. That should do it. And just for fun, let's put one of these 16 microfarad film capacitors on here and see what the leakage looks like on it. I'm going to stick that right there. And I turn the voltage up. And it'll go up. This thing's 250 volts. I could put 100 volts on here. There's 100 volts. And look at that. Nothing. And if I go to microamps, 0.2 microamps of leakage. That's it. And that's the difference between a film and an electrolytic capacitor. That kind of shows you the difference. Now this is rather charged up and spicy right now, so I am not going to put my fingers on it, although some of you would like to see that. And I will discharge it, which at 15 microfarads doesn't take that long. Okay, so that's that. And last but not least, for fun, I just pulled this randomly out of an old bag of old capacitors. This is a 0.25 microfarad paper foil cap. You know, the kind that people love putting in their guitars because they call them tone capacitors, you know, and all that good stuff. So let's turn this up and let's see what kind of leakage we get. I'll put 100 volts on it too. And look at that. We have 16 microamps. And it'll just sit there all day and leak like that. And believe it or not, this is probably a good capacitor because these foil caps would come right out of the box like this. A lot of brand new ones. Paper foil caps have a little bit of inherent leakage. That's just what they do when compared to a film cap. And it'll just, that'll never go down. That is a permanent, it's almost like there's a resistor inside there that just permanently, and you can do the math. If we do the math, if I can find a calculator in order to do said math. So if we do the math with our calculator here, if we take, what is it, 101 volts divided by 0.000015, and you have, what's that? There's 6.7 mega ohms. So you have a 6 mega ohm resistor is what this is being the equivalent of. And of course, really a foil paper cap, you want it to be above at least 20 or 30 mega ohms for it to be not interfere with most of those old circuits. So this would be considered a failing capacitor because that's too much leakage. So you see with a power supply and a meter, you can do the same leakage test as my fancy leakage meter does and all that stuff. So we calculated this to be about a little over 6 mega ohms, right? So Hold on a second. So let's see if I'm right. Or if our calculations are right, I should say. And according to this, yeah, 6 mega ohms. Actually, that would be 10 mega ohms, my bad. Were we on that now? So if the next notch would be 10 mega ohms, and then 15, and then 20. 200 would be 20, so I think that's 10 mega ohms. Let's try it again. Whoop, if I can stay on the meter. Hold on. Come on. Yeah, 10 mega ohms. So this meter says 10. We calculated 6 point something. And of course, this put 30 volts across the capacitor because this has a 30 volt battery in it. And if we use the ohm meter and put the leads in the correct way, we'll put one lead here, one lead here. And as the capacitor charges, it's going to go up. You can see it's probably going to go maybe around 10 megs again. Whoops, if I can keep the probe on the leads. It's still going. So you could see with the very low voltage, this only puts a few volts across that capacitor. So it makes it appear like it's not leaky. The power supply method put the most voltage across there, and of course it let you know, showed you how much leakage. And even this puts 30 volts across the cap, which did give you a better indication that it was leaky. So the way you test capacitors does matter. So what can we say that we learned from all of this? Some of you probably say absolutely nothing. This was a waste of my time. All right, and yep, could be. What I learned from all this was these old capacitors are pretty similar right now to these ones still. The capacitance does read a little bit lower on these, like they've kind of depleted a little bit. But from a leakage and ESR standpoint, they're all very similar. So we probably could put these back in and they would still probably work for some appreciable amount of time. How much time? Don't know. Remember, there's chemistry in here, these chemicals that make the electrolyte and that make the dielectric, and they do have a shelf life. Eventually they will go bad. But these old Nippon Chemicon caps are very, very good quality. So who knows, you may get another 10 or 20 or 30 years out of them. Who knows? The thing you have to ask yourself when you're doing this, if you're refurbishing it for yourself and you know how to do this stuff, leave them in. If you're selling this or you're doing a restoration for someone else, you don't want to have the chance of these failing prematurely, replace the caps. So in this instance, and again, this is mostly for my hobby, I'm going to replace these caps, and that's going to give me an excuse to make up some sort of a solution to be able to fit these caps in place of where these ones used to be. And that's the main reason I'm going to do that. But I don't believe it would change the performance of this amp hardly at all if I left the old caps in versus the new caps. The only difference is these are definitely higher capacitance, and I normally would not do that, but this amplifier has a soft start circuit, so it'll work just fine with this. So I can just drop these in and they will work. Having extra storage, these are being used as filters. Think of them as fancy fast charging and discharging batteries. That is a lot different than a capacitor that's used in a signal path. Different characteristics mean different things for different applications. So if I were using this in something that has a signal path, I would be concerned about changing the values. But since this is being used as a storage capacitor, it's going to be fine. Is this going to be a noticeable difference? Some say they can hear better bass response when they go to a higher storage, higher capacitor. But usually, again, these guys knew what they were doing. You probably do not need anything more than this, and just putting a larger value is just overkill. Since I have it and since they physically will fit, I'm going to use them. But if I replace these with just another set of 12,000s, I think it would work just fine. The other thing we learned was different test methods will give us different results, right? So the LC102 versus the DE5000 versus the using a power supply and putting real power on the capacitor versus using a very low voltage device like this. They all use different methods for testing. They use a different test signal, different amounts of current they'll apply to the cap. With big electrolytics that draw a lot of current when they're charging and everything, that makes a difference when you're testing them. And that's kind of the purpose of this exercise that I did. So I think that's enough for this video. And next time we come back, I'll probably start on doing some of these boards, because I did make up a board for these. I'm waiting for them to be printed and then shipped out. And so we'll get back to this project here. In the meantime, we'll start working on things like this driver board and so forth. And this will be probably a solder and chat. All right, so I'll see you all later. As always, I wish you all peace, joy, happiness, and good health in your lives. And we'll be back again real soon. Take care, everybody. Bye-bye.